Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Okay, so you still stay with me, right? And we are about to continue our last lesson. Okay, so yeah, we'll here. So types of operation. So there are seven types of operation. Okay, so let's just dive into the table. Okay, so here's some common instruction set operation. For data transfer, we have move. It's very straightforward. We have store, load, fetch. We have exchange, clear, reset, set, push, pop. Actually, this is kind of stack operation. We have push and pop. Maybe we'll encounter a detailed explanation about stack later. It's on appendix. I will show it for you later. Okay. Then we have arithmetic operation. Also, there are several: add, subtract, multiply, divide, absolute, negate, increment, decrement. So this is some basic mathematical operations. Okay, it's self-explanatory. For logical is actually, yeah, more or less the same as the Boolean operation that we have discussed. We have AND, OR, NOT, XOR, something test, compare, maybe you don't encounter in Boolean operation. And set control variables, shift, passive, also rotate. Okay, there is a difference between shift and rotate. Rotate this, there is a wrap around and okay, and for this is constant at end. Okay, so you need to pay attention. Then we have transfer of control. We have jump conditional, jump to subroutine. Maybe this is self-explanatory later if we have understood programming. That's why I really want to start to explain programming to you. Return, execute, skip, conditional, halt, wait, no operation. Maybe later in algorithm course I will try to explain it one by one to you. And the input output we have read, write, start IO, test IO. For the conversion we have translate and convert. Okay, and for processor actions for various type of operation, we have data transfer, arithmetic, logical, conversion, transfer of control, IO, and this is what is done. Okay, okay, so here's we cover one by one. So data transfer. Here's what to do. First, the location of the source and destination must be specified. Okay, it could be memory, register, or top of stack. And second, the length of data to be transferred must be indicated. And third, then with all the instructions with operand, then the mode of addressing for each operand must be specified. This is the important thing. Okay, in terms of processor action, then the data transfer operation are perhaps the simplest type. If both the source and destination are registered, then the process simply causes data to be transferred from a register to another, and this is an operation internal to the processor. And if one or both data are in memory, then the processor must perform some or all of the following action. Okay, so calculate the memory address, or if the address is to the virtual memory, then translate from virtual to real, determine whether the address item is in cache, or if not, then issue a command to the memory module. Okay. Next, we have arithmetic. So actually, there are some absolute, negate, increment, decrement. Okay, this is the table basic logical operation that we have covered in the last episodes. Then the execution of the arithmetic instruction may involve data transfer operation to position operand for input to the ALU and to deliver the output of the ALU. We have also logical. Okay, so bit feeding. Okay, so most machines also provide a variety of operations for manipulating individual bits. Okay, or bit feeding. This is an important thing. So it is called a bitwise operation. This is a very important term. So bitwise means that the manipulation is applied to individual bit. Okay. In addition to bitwise logical operation, that most machines provide a variety of shifting and rotating function. With logical shift, then the bits of word are shifted left or right. Okay, on one end, then the bit shifted out is lost. Okay, that is for arithmetic shift. So the arithmetic shift operation treats data as in sign integer and does not shift the sign bit. This is important. So the sign bit is not affected. So on the right arithmetic shift, the sign bit is replicated into the bit position to right, and on the left arithmetical shift, the logical left shift is performed all bits but the sign bit which is retained. Okay, so with numbers in choose complement notation, that right arithmetic shift correspond to division by 2, and for arithmetic left shift and logical left shift correspond to multiplication of 2 when there is no overflow. This is the rule. Okay, and for rotate or cyclic shift, then the operation based of all the bits being operated on, and this is what called a wrap round operation. Now conversion. Conversion instructions are those that change the format or operate on the format on all data. Yeah, this is actually, I'll not cover it. Input output, we have discussed about it, right? We have DMA, memory map, isolated programming. Okay, we have discussed about it. System control. Okay, so system control instructions are those that can be executed only while the processor is in a certain privileged state or is executing a program in a special privileged area of memory. Transfer of control. Okay, so here's some reason why this may take place. Okay, so in the practical use of computer, it's essential to be able to execute instruction more than once and perhaps many thousands of times. Okay, so one sequence of instructions is executed repeatedly to process all the data. Okay, so filter of programs involve some decision making, and that is why sometimes the condition holds, another thing with another condition hold. Okay, and to compose a correctly large or even medium sizes, exceedingly difficult tasks, and we need breaking tasks into a smaller piece that can be worked on one at a time. Okay, maybe you can read it by yourself. Then we have branch instruction. Okay, actually, this may be explained better if we have kind of programming, but we haven't explored programming. Okay, so here's just the theory. So branch instruction, branch instruction or jump instruction has one of its operand address of the next instruction to be executed. Most often, the instruction is a conditional branch, and sometimes it's an unconditional branch. What is the difference? The difference is this. Branch is made only if a certain condition is met, while this one is not attached to a certain condition. Then skip instructions. Yeah, it's self-explanatory. It's just skip the instruction. Okay. There's some typical, for example, increment and skip with 0 IST. Actually, it's all assembly mnemonics. Maybe we'll discuss assembly later. Maybe I'll not dive into depth. I'll kind of explain the important thing. And perhaps the most important innovation in the development programming languages is the procedure. So a procedure is a self-contained computer program that is incorporated into a larger program, and at any point in the program, the procedure may be invoked or called. Okay. So here's the next step: procedures. And the procedure mechanism involves true-based instruction, which is a call instruction that branches from the present location to the procedure, and a return instruction that returns from the procedure to the place from which is called. And both of these are performed of branching instructions. Maybe I want you to analyze this figure. Actually, this is self-explanatory and the explanation is here, but you may need take your time to see, to understand the explanation. Okay, so there are three things worth noting. So first, a procedure can be called from more than one location. Second, a procedure call can appear in a procedure, which require nesting, which allow nesting, and each procedure call is matched by a return in the call program. And there are three common places for storing the return address, which is register, which are registers, start of call procedure, and top of stack. And here are some examples. Okay, the only limitation for two approaches that discussed in the example is that of they complicate the use of re-entrant procedure. Okay, a re-entrant procedure is one in which it's possible to have several calls open to it at the same time. So a recursive procedure, one that calls itself, is an example of the use of this feature. Okay, and there we use a stack, which is more powerful and more general. So when the procedure executes a call, it places the return address on the stack. And when it executes, then it uses the address on the stack and it pops it up. Okay, here's how stacks implemented for nested subroutines. So we call this push. Oh, we call this push, and then the 4601 is pull or pop. Okay, we push and we pop it. Push pop from the stack. Actually, this is self-explanatory. Yeah, and we have some operation types in x86 too, which is actually I will not. Let's skip this. Yeah, this is very kind of machine specific. Maybe we'll not dive into it, except that you want to work for Intel later. Okay. Okay, let's scroll. Okay, let's just dive into new chapter. Okay, mathematics. Oh, here's something interesting. A stack. Yeah. So a stack is an ordered set of elements, only one of which can be accessed at a time, and the point of X is called the top of the stack. And the number of elements in the stack or length of the stack is variable. The last element in the stack is the base of the stack. Okay, and we have what called push down list or last in first out list. Okay, you see we have stack pointer, which always be updated, and we have base pointer, which is the first element of the stack. And we have two operations: push, which appends one new item to the top of stack, and pop, as I have told you before, we have a push and pop. Okay, so pop will remove the top item from the stack. Then here are some implementation of stack. It is part of processor implementation. Okay, so here are some stack oriented operation: push, pop, unary operation, binary operation. See, we have the use free. This is block reserve for stack, stack base, stack pointer, stack limit. Okay, so this is the explanation. So stack pointer contains the address of the top of the stack. Okay, if an item is appended or deleted, then the pointer will be updated. Okay, stack base, it contains the address of the bottom location, the reserve block. Okay, if the stack is empty and pop is issued, then the error is reported. And stack limit is address of the other end of the reserve block. So also a report will be made. An error report will be made if we make an attempt to push when the block is fully utilized for the stack. Also, there are two key attributes for stack implementation, which is ascending, descending, and over. And I want you to read it by yourself. Then we have expression evaluation. It's called an infix notation. Okay. Also, we have another technique called the postfix notation. This is actually sometimes important. Okay, so the advantage of the postfix notation is that expressing the font is easily evaluated using stack. And here's the two rules that apply in postfix notation. Maybe we'll not dive into very great detail like this. Let's go into little, big, and by-endian. So it's about by ordering. So the concept on DNS was first discussed in a lecture by Cohen. So with respect to bytes, the NDNS has to do something with byte ordering of multi-byte scalar value. For example, you see, we want to store 32-bit hexadecimal value 1, 2, 3, 4, 5, 6, 7, 8, and there are two ways we store it. Okay, this is the lowest address. This is the highest address number. Lowest address number, highest address number. We can store from the lowest to highest, or from the highest to lowest. So the mapping on the left store the most significant byte in the lowest numerical byte address, and this is called the big endian, or left to right order. While mapping on the right stores the least significant byte in the lowest numerical byte address, and this is called the little endian, or right to left order. And this is the difference. But this makes problem, right? If we don't do this proper, if we don't understand the endianness of the machine that we are operating with, then there will be some chaos in the operation of read-write, because we will wrongly take the data or store the data. So this must be a really crucial and critical constraint. Okay. And there is no general consensus as to which is the superior style of endianness, and the following points favor the big endian style, which is with character string sorting, decimal IRA, dumps, and consistent orders. And the following favors the little endian. Okay, a big endian person has to perform addition when it converts 32-bit integer address to 16-bit integer address, and it's easier to perform higher precision arithmetic with the endian style. You don't have to find the least significant byte and move backward. Now, bit ordering. So in ordering the bits within a byte, then we are immediately faced with two questions. Do you count the first bit as a bit 0 or as a bit 1? And you assign to be a little endian or big endian. Okay, so here's the issue that we face now. And I want you to, maybe this is your homework, to review about this question, and yeah, maybe you may tell me your answer in the comment section. Maybe you can propose, you can suggest something related to that two questions. Now let's learn about instruction sets, addressing mode, and functions. So an operand reference is an instruction either contains the actual value of the operand, immediate, or reference to the address of the operand. The wide variety of addressing modes used in various instruction sets. This include direct, indirect, register, this is indirect, various form of displacement, and an instruction format defines a layout field at the instruction. Okay, and this is something that is quite complex. So in previous chapter, we focus on what an instruction set does, and now how to specify it. Okay, so this chapter focus on explaining about how. And first thing is to solve is addressing. So the address of fields in a typical instruction form are relatively small, and if you want to um, able to represent a large range of location memory or process virtual memory. There are some addressing techniques that may be used. We have immediate, direct, indirect, register, indirect, displacement stack. Let's see if I can explain to you in this episode all of this, or maybe we'll cut it. Okay, so immediate, direct, indirect, register, indirect, displacement stack. Let's review first. And this is the summary table. Maybe you want to take a screenshot first, and later when we are going through discussion, then maybe you can uncover this table, what this table means. Okay. Okay, so before beginning the discussion, two comments need to be made. So first, virtually all computer architecture provide more than one of these addressing modes, and several approaches are taken. Often different opcode will use different addressing modes, and also one or more in the instruction format can be used as a mode field, and the value of the mode field determines which addressing mode is to be used. And the second comment concerns the interpretation of the effective address. And a system without virtual memory, the effective address will be either a main memory address or a register. And in a virtual memory system, the effectiveness of the address in the virtual is a virtual address or register, which is function of MMU, Memory Management Unit, and is invisible to the probe. Okay, first one, immediate addressing. So this is the simplest one. Okay, so operand value is present in the instruction. Operand equals A. Okay, so this can be used to define and use constant or set initial value of variable. So we just immediate addressing. The advantage of this is that no memory reference other than the instruction flag is required to obtain the operand, thus saving one memory case cycle and the circuit in the instruction cycle. But the disadvantage is that the size of number is restricted to the size of the address field. Okay. Next, we have direct addressing. Okay, so EA equals A. If before we have operand equals A, now we have EA equals A. A is actually address. Okay, so the address field contain effective address of the operand. So effective address EA. So the technique was common in earlier generation of computers, but it's not common in contemporary architectures. So it requires only one memory reference and no spatial calculation. So the limitation is that it provides only a limited address of space, a limited address space. And the next is indirect addressing. When we are dealing with the previous one, the addressing, the length of the address field is usually less than word length, thus limiting the address range. And one solution proposed is to have the address field refer to the address of a word in memory, which contains a full length address of the operand, and this is called indirect addressing. Okay, so EA equals A in parentheses. It means this address of a word in memory. Okay, indirect. Okay, so the parentheses are to be interpreted as meaning contents of. Okay, contents of. The obvious advantage is that for a word length of n, an address space of 2 to the n is not available. But the disadvantage is that the instruction execution requires two memory reference to fetch the operand. Once to get its address and execute is to get the value. And sometimes we use very often that indirect addressing is in the multi-level or cascaded indirect addressing as shown. And maybe we have indirect flag. If the I is 0, then the word contains the EA. If I is 1, then another level of indirection is involved. This, recursion. Okay. Then we have register addressing, which is similar to the addressing, and the only difference is that it refers to register rather than a main memory address. Okay. The advantage to this is first, only a small address space is needed, and second is no time consuming are required. Okay, why it's very hard to operate this computer. Okay, so if register addressing is heavily used in instructions, that this implies that processor register will be heavily used, and there are limited number of registers they're used in fashion makes sense only if you employ effectively. Okay, see, the disadvantage is register addressing is that the address space is very limited. Okay, see, if instead the Next is register indirect addressing. Okay, for this one, this is analogous to register indirect addressing. Okay. The only difference is again whether the address field refers to memory location or register. Okay, EA equals R in parentheses. The advantage and limitation of register indirect addressing are basically the same as for indirect addressing, and in both cases, the address space limitation of the address is overcome by having the field refer to word, length, or location containing address. Okay, and you use one less memory reference than indirect addressing. After it, we have the displacement addressing. This is a very powerful mode of addressing, combines the capability of direct addressing and resistant direct addressing. Okay. So displacement addressing requires the instruction have two address fields, at least one of which is explicit, and the value containing one address value equals A is used directly, and the other one, implicit, refers to a register whose contents are added to A to produce an effective register. Okay, so there are three common uses of displacement addressing, which is relative, base register, indexing. Relative, okay, I'll call PC relative addressing. Then we have the implicit reference register, the program counter. Next instruction address is added to the address space for this AI, and typically the address space is treated as a two's complement number for operation. Thus, the effective address is displacement relative to address of instruction. Then we have base register addressing. And the interpretation is the following. The reference register contains a main memory address, and the address field contains a displacement from the address. And the register reference may be explicit or implicit. And for indexing, then the interpretation is following. The address field represents a main memory address, and the reference register contains a positive displacement from the address. And this is just the opposite of the interpretation for base register addressing. Okay, because the address space is considered to be a memory address in indexing, it generally contains more bits than an address field in comparable base register instruction. Okay, we have what called index register, which is initials to 0. Okay, because index registers are commonly used for such iterative tasks, it's typical that there is a need to increment or decrement the index register after its reference to it. And this is what called an automatic. If we are having automatically mechanism as part of the instruction cycle, this is called auto indexing. This is shown as stated in the example. We have post indexing, pre indexing. Okay, next one is we have stack addressing, and I think this is the last discussion for today. Okay, so for stack addressing, okay, because we know that stack is a linear array of location, we have push down list and LIFO, okay, LIFO queue. Then the stack is a reservoir of location that items are appended to the top of the stack. Okay, so which associated with the stack is a pointer whose value in the address of top stack. So yeah, the stack pointer is maintained in a register, thus reference to stack pointer in memory are in fact indirect addresses. And the stack mode of addressing is for implied addressing, and the machine instruction need not include memory reference, but implicitly operate on the top of the stack. Okay, let's see. Maybe okay, not so very important. Yeah, there are actually quite many things to cover. Okay, for instruction format, I will leave it for the next video. Okay, I think that's for today. We are enough. Yeah, nearly 30 minutes. Okay, so here's a little quote I can share with you today. So, catfish hunters say, winning isn't everything, but wanting to win is. Okay, it means actually don't stop even if you win and achieve some great achievement one day, because we are still in the way to reach our true success. Okay, so thanks for watching. And that's all our lesson for today. Thanks for watching. And here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https colon/science.xyz.unux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.